To summarize again, in the basic backpropagation algorithm, a single step means we start with the current weights and biases. We feed in the data input and have the model produce outputs. We calculate the cost, which is the difference between what the model is predicting for the data we just fed in and the prediction we want the model to produce from this input. We use the chain rule to calculate the gradient for all the weights and biases in each layer of our network. We update the weights and biases in proportion to the negative gradient. These steps are repeated over and over again until learning converges to a minimum of the cost function. One more concept I want to add here is the concept of a learning rate, which is the number we multiply the gradient by, which tells us the exact amount we will change each weight and bias. The gradient told us proportionally how much we want to change the weights and biases relative to each other, but the learning rate tells us overall how much we'll scale the gradient by when we make our updates. One of the variations for learning, which I briefly mentioned before, is to vary the amount of data used when calculating the cost and gradient at each step of learning. Remember, the gradient tells us how the cost function changes in response to changes to each of the weights and biases given the current values of weights and biases in our network. For each step of learning, we calculate the negative gradient, and this tells us proportionally how much to change each of the weights and biases to decrease the cost. I had said that theoretically, we want to be minimizing the cost for all of our training data. This means using all of our training data to calculate the cost and gradient in a single learning step. And that's known as batch learning, where we use all our training data in a single step of learning. This is the most theoretically accurate way to proceed, and is even guaranteed to find the minimum of the cost function under certain conditions. However, a training set can have hundreds of thousands or even millions of examples, and using the entire training set in every learning step becomes very slow, and it's often not even feasible to load the entire training set in order to compute the cost function and gradient calculations at once. Another problem with using the entire training data set for each step is that the data could be very similar to each other. So when you're using the entire training set all at once, and then you calculate the cost and gradient, there can be redundant information, and so you're not really getting the bang for your buck for using the entire data set because a lot of signals are being repeated. This is why deep learning researchers often don't use all of the data in a single learning step. At the other extreme to batch learning, which is using all the data in a single learning step, we have stochastic gradient descent, which means we only use one training example to calculate our cost and gradient at each step of learning. This means in a single learning step, all the weights and biases are updated so that the neural network becomes better at predicting just that one training example, because the gradient was only evaluated based on that one training example. The advantage of using just one example is that we don't have redundancy because there is only one training example being used. It's also very computationally light to calculate the cost and gradient for just one example. Also, by not using the whole training set at every step of learning, this helps our model not become overly specialized just for our training set, and this helps prevent overfitting, which is the problem we talked about in our last lecture, where the model becomes overly specialized to its training data and becomes less good at generalizing to new data. The disadvantages of using just one training example is that we're not as guaranteed to find the minimum of the cost function as we were when we used the entire training set. Because we don't have as strong guarantees of converging to the minimum of the cost function, we need more tricks for adjusting the learning rate and changing the learning rate as we learn. Finally, we have something in the middle of batch learning, where we use all the data, and stochastic gradient descent, where we use only one data example for each step of learning, and this is known as mini-batch learning. Here we use a portion of the data, so it might be, say, 10 or 100 examples to calculate the gradient at each training step. Typically, our mini-batches are pretty small relative to the size of the entire training set, so mini-batch learning, with its relatively small batch size, shares similar advantages and disadvantages to stochastic gradient descent, where we just use one example per learning step. However, if we did move towards very large batch sizes that were getting towards the size of an entire data set, for example, then we start sharing the pros and cons of using batch learning, where we used the entire data set. An additional advantage of mini-batch learning is that the gradient computations can be made using a vector representation, similar to the vector representations we talked about in our linear algebra interlude before. Vector representations allow computers to apply computations to many data examples at once as fast as computing on a single data example. And you might wonder, why can't we use efficient vector representations for batch learning when we use the entire data set? Well, it's because the entire data set is usually too large to represent as a vector in computer memory. But for mini batches, this is possible, and we can take advantage of this efficiency. There are also other variations to the basic backpropagation algorithm. These variations are specific tricks designed to help the neural network find the minimum of the cost function more effectively. I won't go into the details of each of these variations, but here are some names in case you see them in the future and you'll have an idea of where they fit in the scheme of things. Momentum is a very common variation to backpropagation. Attgrads, RMSprop, Atom, and then there are also much more. These basically do a variation on backpropagation. So they do something very similar. They do calculate the gradient using backprop, but they do variations on this. Like they might be averaging the gradient values that were calculated with backprop, but averaging it over many previous training steps. Or they might have different ways of changing the learning rate throughout the learning process. Beyond finding the appropriate values of weights and biases for our neural network, there are other decisions to be made when building and training deep learning models. We won't go into the finer details, but I'm going to give you an overview of the other considerations here. Some decisions that need to be made about the learning process are the batch size, which, as I mentioned, you could use anything between one data example, known as stochastic gradient descent, to the whole training set, known as batch learning, but also something in between, which are mini batches. Choosing the wrong batch size can cause the model to not converge. We also have to choose the learning rate, which is the number you multiply the gradient by when updating your weights and biases. Again, this can make or break whether your model ever learns anything useful. For our other variants in backpropagation, there are parameters that tell us how to vary the learning rate for different weights and biases over time. So this is another parameter that needs to be chosen or discovered. For the variants on backpropagation that involve averaging the gradient over many time steps, we have parameters that would tell us how to weight the past time steps in this average. We also have higher level architectural decisions that we need to make about our neural networks, like how many hidden layers we want, how many units we want in each layer, and choices of activation functions. Applied deep learning is a very empirical process. Mostly we would just try something, see how it works, and then iterate. Sometimes you might be able to port your intuitions from a previous problem in a different domain to the current problem that you're working on. But usually, you often have to just start learning from scratch in a new domain. So the intuitions that you might learn from building models for, say, self-driving cars would not help you when you're building an Atari game or doing speech recognition.